Good. Hello, good morning. Statistics for data science. We are in the frequentist inference part, and today the topic is asymptotic estimator properties. And for myself, this was one of the most challenging lectures of this course because I'm novel to it. So I knew that these things existed before, like consistency and efficiency, but I looked at what they meant at one point in my life, but I never really worked with them, so I really had to work somewhat for this lecture. So the good news is, at least for me, after this lecture, things get a little bit less complex again, which is something. So last time we talked about finite sample estimator properties, and we introduced bias and variance of estimators and the Kammerau bound, and this was all under the assumption of a fixed sample size n. And the main thing today is then to let n tend towards infinity. This is the stuff that I based things on. The most complex things in the end, I think, are the proof of the consistency of maximum likelihood estimators and asymptotic normality of maximum likelihood estimators. And this I took from the Held book and worked with that. So maybe that's the first starting point in your reading. Who actually, has anyone read what I always put here? Who has read anything of what I put here? No, from all the lectures. So I always have bibliographic remarks. Has anyone ever opened these books? Yeah, good. And which is your favorite book? Wassermann. Okay. Any other favorites? No, good. Okay, but you read it. I mean, at least you are the ones who show up, and so I don't know what the other ones are doing. But read the stuff definitely, because I try to kind of streamline things, but of course I'm also leaving out a lot of things, and specifically examples and so on. And definitely the course is more than just the slides, although of course the exam will just be based on the slides. But to really get most of the course, it makes sense to read at least what I put here from these books. Good. So asymptotic statistics you find in all of the books that are mentioned. What is the whole thing about? Well, it's asymptotic statistics, which you can also view as a kind of a research field. So when we talk about asymptotic estimator properties, what we're looking into a little bit and scratching on the surface is this field of asymptotic statistics. And we are here, of course, mainly concerned with the question of estimators and their behavior for large sample sizes. And asymptotic statistics is all about these large sample sizes. Interesting. Why is this interesting? So there are two aspects to this. The first thing is that we can understand the qualitative properties of estimators more, and essentially also introduce some optimality properties of maximum likelihood estimators. So maximum likelihood estimators are, of course, very prominent in data science. And we discussed the intuition, and that intuitively this kind of makes sense, but it's also nice to know that there's quite a lot of theory that shows that under some regularity conditions, which will be the Fisher regularity conditions that we previously introduced, they actually have some optimality properties. And that's good, because then it makes sense to do maximum likelihood estimation, be it in a numerical setting or an analytic setting. The other thing is, besides these kind of optimality issues of, for example, maximum likelihood estimators, specifically looking at asymptotic distributions of estimators also allows to use distributions in the large sample limit to construct, for example, things like confidence intervals and certain hypothesis tests. And we will use, for example, the asymptotic normality of maximum likelihood estimators in the next 2 lectures on confidence intervals and hypothesis tests to construct certain confidence intervals and certain hypothesis tests. So there are these 2 aspects. One thing is optimality of maximum likelihood estimators, essentially. The other thing is that we get large sample approximations in terms of distributions, and we can use them down the line to use to construct confidence intervals and hypothesis tests. Why do I think it's interesting? Well, big data, large sample sizes, I guess. I don't really know what big data is supposed to mean. I mean, I read what people think what it's supposed to mean, but I mean, big data definitely has these 2 aspects, that you have many features. So you have big, large random vectors, and then you have many realizations. And of course, if you have many features and then you don't have that many realizations, then of course you again have some kind of curse of dimensionality problems. But if you have kind of, if the ratio in terms of data points and so realizations and dimensionality of your feature vector is kind of large, meaning that you have that your sample size is actually large with respect to the dimensionality of your feature vector, then definitely you're in kind of some asymptotic regime where you have just a large sample size. So from my perspective, looking at asymptotic statistics is both practically useful and justified, because in the era of big data, we have large sample sizes. That's what I would say. It's not what, so I think the mainstream says big data, we need machine learning. That's kind of the mainstream, and I don't hear much about asymptotic statistics. I also looked around a little bit. Maybe it hasn't entered the mainstream, or I'm fundamentally wrong. Any opinions on that?
I have a question. Like big data, as I understand it, is more about what we can compute, or one definition is big data is that you can't put it on one computer, same like in one memory. But how does it map to statistics? What does very large mean in statistics?
Yeah, that's what I just tried to explain. So many realizations, many data points in terms of realizations of random variables.
But like relative?
Yeah, more than 30.
More than 30, okay.
A million.
Pretty low bound.
Yeah, or a million.
Yeah.
So, I mean, what you, of course, what I assume you know is that classical statistics was developed in the early 20th century in kind of this 0 to 30 data points regime, because this is when the t-distribution is still different from a normal distribution. After 30 data points, the t-distribution is virtually identical to a standard normal distribution. Well, I mean, maybe a little bit more, but definitely statistics was developed more in the low data point scenario. And hence classical statistics in the asymptotic sense, of course, was more kind of an academic exercise, because you didn't really let data be a lot larger than 50 realizations. And now, of course, you have really many realizations. But then it also depends, and this is why I also don't, this term big data doesn't really mean much from my perspective, because it's always the question of are you talking about random vector dimensionality? Are you talking about the realizations and so on? Anyway, we are not, so I'm just saying that if somehow in big data you have the case that the sample size is actually large, also with respect to the dimensionality of your random vector, then definitely asymptotic statistics makes sense. And large means here, 1,000, million, billion, so large. If you want an introduction to this whole asymptotic field, statistics fields van der Waart, that's a nice, or it's a comprehensive introduction. So this is kind of the background, and now as a summary and as a overview, what will we discuss? So we are interested still in parametric statistics and estimating the properties of a model, which is of course the same thing as learning the parameters of a neural network, but this still needs to diffuse into certain brains. So let theta hat be an estimator for a parameter theta of a statistical parametric model, and let this parameter estimator be based on a random sample of size n. And here we have our random variables, which of course are the theoretical constructs behind our observed data. Now, what are asymptotic properties of the estimator in this setting? And this is what follows on the slide. First of all, theta hat is called asymptotically unbiased if, for large sample sizes and going to infinity, the expected value of the estimator corresponds to the true but unknown parameter value. Yeah? We already saw unbiasedness last time, which was the case that for any sample size, the expected value of the estimator corresponds to the true but unknown parameter value. So asymptotically unbiasedness is a little bit weaker. It says at least if the sample size gets very large, then our estimator is unbiased. So that's asymptotic unbiasedness. Then there's this property of consistency. So an estimator theta hat n is called consistent intuitively if, for large sample sizes n going to infinity, the probability that the estimated theta hat n deviates from the true but unknown value becomes small. Always note that how this works. So n is going to infinity, and this estimator is based on n random variables, meaning on n realizations of your data. Yeah? An estimator theta hat n is called asymptotically normally distributed if, for large sample sizes, the distribution of hat theta n is given by a normal distribution. Makes sense. It's called asymptotically efficient if, for large sample sizes, the distribution of hat theta n is given by a normal distribution, and now with expectation corresponding to the true but unknown parameter value and variance corresponding to the reciprocal of the expected Fisher information, which is, as we established last time, the Kramer-Rao lower bound. So asymptotically efficient is more than asymptotically normally distributed. It makes it embodies certain constraints on the parameters of this asymptotic normal distribution. And finally, about maximum likelihood estimators, for which you can also say these kind of criteria were invented. Maximum likelihood estimators actually fulfill this, so they are asymptotically unbiased, consistent, asymptotically normally distributed, and asymptotically efficient. In a way, calling them asymptotically efficient, of course, also implies that they are asymptotically normally distributed, asymptotically unbiased, and consistent, not quite. So this efficient is kind of a maximum property that includes definitely asymptotically normally distributed and asymptotically unbiased. So that's the overview, and in the rest of the lecture we now want to go a little bit more into the details of these criteria and what they really mean. Yeah. So who has studied these before? No. Oh, so that's novel to everyone, not only to me. I mean, who has heard them? Who has heard something like consistent estimator? Also no. I've heard them before. So, first we want to discuss these criteria in a little bit more detail, and then discuss maximum likelihood estimator properties, because these criteria, of course, they apply to any kind of estimators. And then the question is, that we are interested in looking at here, what about maximum likelihood estimator with respect to these criteria? And the first thing is asymptotic unbiasedness. And so we will go about the definitions and then look a little bit into examples and understanding the definitions in this first part. So this will always be the scenario, so I'm writing it up always, but of course you can, when you study that, clarify once for yourself what this is supposed to mean, and then you can just read over it in all the definitions, because it's always just there to establish some ground, but it doesn't really carry much information then once you clarified what it means. Again, keep in mind that this theta hat n is an estimator for the true but unknown value of the parameter theta, and it's based on n data realizations or n random variables that lie behind your data realizations. So what does asymptotic unbiasedness then mean? It means that the limit of the expected value of theta n under, of course, the expectation formed under the true but unknown parameter value equals theta, and it does so for all values of the parameter. Yeah? So if it's just for one value, then that's not enough to be asymptotically unbiased. It needs to hold for all possible parameter values. This is again the intuition. So asymptotically unbiased estimators are unbiased in the large sample limit. So recall that unbiasedness means that the expectation under the true but unknown parameter value of the parameter estimate equals the true but unknown parameter value. This is now made a little bit weaker, that it's only holding in the limit of n going to infinity. An unbiased estimator is of course necessarily asymptotically unbiased because it's already unbiased for low sample sizes like 1 or 2. This is an example for an asymptotically unbiased estimator. So here we assume we have n random variables distributed according to a univariate Gaussian. And they are IID, which I didn't really have to put in here because this is always supposed to mean that things are an IID, so that is a random sample. And what we're looking at is our maximum likelihood estimate of the variance parameter. Yeah? So note that this is not the sample variance, but it's the maximum likelihood estimator, which I may have previously mentioned that it's biased. And we will see that again. The good thing is that it's biased, but it's asymptotically unbiased. And yeah, this is one way to look at that. So what we have seen when we discussed the unbiasedness of the sample variance is that the expected value of this thing here, essentially, so we take the 1 over n out, and we looked at the expected value of xi minus the sample mean squared and the sum of that, this was given by n minus 1 sigma squared, which is not sigma squared. Yeah? So this is why this multiplying this thing here in the brackets with 1 over n minus 1 gives you an unbiased estimator, because the expectation of this thing alone is n minus 1 times sigma squared. This is what we've shown already. In this case we have this additional thing that we divide by n. This just recapitulates that the maximum likelihood estimator for the variance parameter in a Gaussian is biased. However, if we now allow n go to infinity, then because the limit of n minus 1 divided by n is 1, we get in the limit the true but unknown parameter value. So of course, intuitively you can think that if you let n be very large, then this minus 1 doesn't contribute anything to this ratio anymore, and you have like a million minus 1 and divided by a million, which is roughly 1. It's not quite 1, but it's roughly 1. So This is in a way good news for the maximum likelihood estimators of variance parameters. So while they are biased for, and of course the bias is strongest if there are a few data points, if you let n go to infinity, essentially using the unbiased estimator in terms of the sample variance or using the maximum likelihood estimator is equivalent, because you will recover the true but unknown variance parameter. Yeah? Questions on this? Happy? Good. So this is, in a way, I think this is good news for maximum likelihood estimation, which is, of course, always with this variance parameter in the Gaussian case, you feel a little bit like, oh, now I established maximum likelihood and it's not unbiased, so why did I do all of this? Well, if you then relax a little bit and say, asymptotically it's unbiased, then it's fine again. That was our quick discussion of asymptotic and biasness. Next up is consistency. So again, we are in the setting of this parametric statistical model. Everything is the same. And now we talk about consistency. And consistency, first of all, needs to be, or it is first, or it's the proper, how do I say it? The original, whatever definition of consistency is in terms of a sequence of estimators. So what is actually converging here is a sequence of estimators, but then you call the sequence then consistent, but because the sequence is consistent, you then also call the estimator itself consistent. So a little bit slower. If you now assume a sequence of estimators, theta hat 1, theta hat 2, and so on, which of course are always based on one more data point, slash one more random variable that you think your data point is a realization from. This sequence of estimators is called a consistent sequence of estimators if for every epsilon larger than 0, that you of course can make very small, and every theta in the parameter space, the limit of the probabilities that theta hat n deviates from the true but unknown parameter value is smaller than theta, is smaller than epsilon here, smaller than epsilon, is 1. Yeah. So the important thing here is that you talk about probabilities. You talk about the probabilities of the event that the estimator theta hat n deviates from the true but unknown parameter value by a really small value epsilon that you can make smaller and smaller and smaller. It needs to be larger than 0, but you can make it smaller and smaller. This sequence of probabilities, this tends to 1. You can, of course, reformulate that in terms of the deviation being larger or equal to epsilon, because these are complementary events. So if this event happens, then this event does not happen. So it has the complementary probability in the limit, which is 0. Yeah? If theta 1, theta 2, and so on is a consistent sequence of estimators, then, and this is what I meant earlier, then theta hat n is referred to as a consistent estimator. So this we can discuss in a second. The convergence type here, and this is one of the things that, the people who write probability and statistics books are very, of course, keen on. This is convergence in probability. We've seen that before, so always keep in mind when one talks about convergence of random variables, there are different forms of convergence, and I think we've seen most of them. So we've seen convergence in probability before. Convergence in probability is always that you have a limit of probabilities of something, and we've already seen things like convergence in distribution, where it's about the CDF, and we've seen the convergence, so almost sure convergence, where it's about the probability of some limiting process. Yeah, but this you should always you will always find that you need to be specific when you talk about convergence, what kind of convergence you're referring to. So again, intuitively, what does that mean? So as n goes to infinity, the probability that theta hat n is arbitrarily close to theta becomes high. So arbitrarily close, meaning here that the epsilon you can make that really small. That it deviates from theta becomes 0. In this scenario, you might even think about making the epsilon large. It still holds. And this is for all true but unknown parameter values. And again, this is convergence in probability. Yeah? So you can also say this quicker than writing this out. You can also say if the sequence of estimators converges in probability to the true but unknown parameter value, because this is the definition of convergent probability, then it's called consistent. Yeah? And we will use this shorter definition of consistency later on, because this is just spelling out what convergence in probability means or how it's defined. Yeah, and now if you want to show that some estimator is consistent, you can either directly test whether your estimator fulfills this criterion with the limiting process. I had an example for that in there from the Casella book, which for the moment I left out because I didn't find the time to really prepare that in depth, because I was busy with the maximum likelihood estimator properties. So one way is to really apply this limiting operation and look at these in detail, where you basically need to compute the probabilities of these events. So in the Casella you find an explicit example for that. Another way you can show consistency is using mean squared error criteria. Using the mean squared error as we defined it last time. And this criterion works as follows. So if the mean squared error of your estimator for n going infinity is 0, then your theta hat n is a consistent estimator. And this is of course helpful because I will show you that in a second, but this is of course helpful because we've already seen the bias and variance decomposition of the mean squared error. That means we can also look at the bias in the limit of large data samples and the variance of the estimator in the limit of large data samples. And if both of them go to 0, then because of the bias variance decomposition, then also the mean squared error goes to 0 for large samples. And we have consistency. So we can basically, without applying the consistency criterion in terms of the probabilities, we can look at our bias, and of course if the bias goes to 0, we have an asymptotically unbiased estimator, and we can look at the variance, and if this also goes to 0, then the mean squared error goes to 0, and hence the estimator is consistent. So first of all, why does this hold? So this, so why does the mean squared error have anything to do with consistency? Well, this has to do with the fact with Chebyshev's inequality that the Chebyshev's inequality says that this probability here is always smaller or equal to this entity here, which is just the mean squared error. Now, if you talk about limits and you assume that the limit of the mean squared error is 0, because this is always smaller or equal to, then of course in the limit this is also 0. Yeah. So if you have mean square error, if you have the mean square error going to 0, then also this event that there's a deviation is by Chebyshev's inequality is in the limit 0. Yeah. Now this, if now mean squared error goes to 0, and of course this implies that the bias goes to 0 and the variance go to 0. So this is briefly written up here. That's fairly straightforward. Let's look at an example. So here we have the sample mean, and in the casella you can read, and this is what I originally had included, you can apply the consistency criterion to the sample mean and directly show that it's consistent, but you can also make your life a little bit easier and know, and we've already studied that, we have seen that the bias of the sample mean, so we are talking now about the sample mean in the scenario of univariate Gaussian random variables, that the sample mean is unbiased. Yeah, so hence it's also asymptotically unbiased, and because it's always 0, it also for infinity, n going to infinity, it's 0. And the variance of the sample mean, we've seen last time that this is given by sigma square, so the true but unknown parameter value divided by n. Now if we assume finite variance, which we of course do when we're in the Gaussian case, then if n goes to infinity, then of course we divide by ever larger values n here, and this goes to 0. So both the bias and the variance of the sample mean go to 0 for n going to infinity, or always are 0 in terms of the bias. Hence the mean squared error goes to 0 for n going to infinity, hence consistency is established. Yeah? So this is a way to really, in a simple way, establish consistency without going into the detailed definition of convergence in probability. Good. Questions about consistency at this point. Convergence in probability. So if you want to understand consistency, the important thing is to understand convergence in probability. Asymptotic normality. Again, parametric statistical model, and now we assume there's another random variable which we call here theta tilde, and this is distributed according to a univariate normal distribution with expectation parameter mu and variance parameter sigma square. Again, like I introduced last time, so essentially all the time the parameter here is scalar. You can of course expand things to multivariate parameter settings, but then of course yeah, you need to be more careful and so on, and then notation becomes more involved. So we are happy with the scalar case, or at least I am happy with the scalar case this year. Now, an estimator in this setting is called asymptotically normally distributed if this estimator converges in distribution to theta hat n. Yeah? So different convergence type, also completely different meaning in a way of what's happening, because convergence in probability is the convergence of a sequence of random variables to a random variable, or in the case that we are looking at, to a value, so a fixed value, which is a random variable which is constant. And this is of course different. I'm talking about this probability to say something about the distribution of the estimator. Now it converges in distribution and to theta hat, and then it's said to be asymptotically normally distributed, for which we write theta hat n is distributed according to this, and we put a little a on top to emphasize that this only holds in the limit of n going to infinity. Yeah? So of course we can always talk about parameter estimator distributions if we study how the data is distributed and how this data is then turned into the estimator by means of random variable transformations, and then we can find the exact distributions of parameter estimators. Here it's about if the sample size gets very large, then this is an estimator is asymptotically normally distributed. this is just a reminder of what convergence and distribution means. That means it's a statement about the cumulative distribution functions that for n going to infinity become identical to the cumulative distribution function of theta. If we later see a implementation of the central limit theorem, I think that's one exercise for today. We should also see a picture of how this then looks in terms of the CF convergence. Oops, there's nothing else on asymptotic normality. Yeah, so it's about the distribution of an estimator that for large samples becomes normally distributed. Finally, asymptotic efficiency. Before we talk about maximum likelihood estimators. So again, setting of a parametric statistical model. And now we also include the expected Fisher information of the random sample x1 and x2 xn. So remember that we discussed expected Fisher information last time. It will come up in most lectures, I think, from now on. So yeah, in a way, make sure that you're happy with Fisher information, expected Fisher information, and also point out if I still have some mistakes in my definition of Fisher expected and observed Fisher information, because that might be the case. I'm trying to get rid of all of them, but I hope it's roughly okay. If now an estimator is asymptotically normally distributed and has as its expectation the true but unknown theta parameter, and as its variance parameter the inverse of the expected Fisher information of the random sample, so this m should be here on this n, it's a little bit off, then theta hat n is said to be asymptotically efficient. So as previously in the overview, asymptotic efficiency means asymptotically normal plus expectation parameter is the true but unknown parameter plus variance parameter is the inverse of the, or the reciprocal of the expected Fisher information. So this is what asymptotic efficiency means. So it implies asymptotic normality, of course, because there's a normal distribution. It also implies asymptotic unbiasedness, because this is the expectation, and in the limit, the expectation of this is hence theta. The variance here, the variance parameter is called asymptotic variance. This is actually what we could have also already established here. So this is the asymptotic variance. For some reason I thought I would introduce it here. And the main reason why I introduced it here is because to have a name for this, and the asymptotic variance in this case of an asymptotically efficient estimator, of course, attains the Kramer-Rao bound, because the Kramer-Rao bound was the reciprocal of the expected Fisher information of the sample, as we've seen. And there is some variations in terms of efficiency. If you go over the different books, I think this is still the most common. It's a little bit hard to, of course, disentangle efficiency and asymptotic normality, because efficiency always implies asymptotic normality. Yeah. Good. This was already the first part of the lecture, so I think the second part we definitely do after a break. So these were essentially definitions, and of course everything that came after this was not really new information, but it made the information a little bit more precise. And yeah, so this overview tries to intuitively link the notions of convergence in probability and convergence in distributions that underlie consistency and asymptotic normality / efficiency. Questions about this first part? I mean, it's definitions. What should one really ask about it? But of course, it needs some getting used to these definitions, because they are, at least these convergence things, has to, yeah, differentiate them in one's head a little bit. Yeah, so then the next thing in the next hour would be to look at the maximum likelihood estimator and now see how maximum likelihood estimators actually perform in terms of their properties, both actually with respect to the finite sample properties that we discussed last time, but mainly about the asymptotic estimator properties. Questions? No? Then have a break.
Yeah.
Okay, then hello, let's continue with talking about the maximum likelihood estimator, because now we established over both this lecture just in the last hour and last week we established quite some criteria, and the estimator that we looked into before that was the maximum likelihood estimator. So now, of course, the interest is how does the maximum likelihood estimator perform, and as of course I already previously announced, it performs very well. So this is the basic result, which is then kind of looked at in detail in the remainder of the lecture. So under the Fisher regularity conditions, maximum likelihood estimators are not necessarily unbiased, we've seen that, but they are consistent, asymptotically normally distributed, asymptotically unbiased, and asymptotically efficient. And yeah, so in a way you can view what we've done in the last hour and last week, also mainly establishing these criteria to say that our maximum likelihood estimator fulfills most of them. So yeah, on the other hand, maximum likelihood estimation is just a very prominent approach for maximum for parameter estimation, and then to establish that theoretically this procedure makes a lot of sense is also good. Yeah, so then it's kind of justified to use maximum likelihood estimators, and it's not and one can, if one's setting up a maximum likelihood estimation scheme, one feels good because one can always say, yeah, theoretically this is very well justified. Thing is that this holds under the regularity conditions, and then the mathematics starts to get quite involved. So in some books, for example, I recently bought this Shervish book on theory of statistics, because this is where Wasserman copied most of the stuff from. So they are all in Carnegie Mellon, so they have quite a old and very good statistics department, and Mark Shervish has his own book on theory of statistics, and he discusses some examples for maximum likelihood estimators which are not consistent, and they are not consistent because these Fisher regularity conditions not hold. So there are certain conditions that, these are the Fisher regularity conditions that need to be fulfilled so that this holds. So in a practical setting, you might then really want to check whether these hold, but then really, no, you don't want to do that. You just want to have an awesome result and a flashy figure so that people believe you because it looks awesome. So these are the properties of maximum likelihood estimators, and now we want to look at them in some more detail. So first, the non-necessary unbiasedness we've now repeatedly discussed. I put it here again in some different notation, which is not really helpful. It's the same thing, stating that the maximum likelihood estimator for the variance parameter in a Gaussian is not unbiased. We've seen it before. I think I had this slide in there before I established the other things. This is why this is still showing up. Yeah, we don't really have to talk about it at all. Restricted maximum likelihood is a way to get to unbiased variance parameter estimates. something we will discuss in the other course actually. So there is, maybe this is also one thing to say, we are talking now about maximum likelihood estimators, and of course they are the most popular and most prominent framework for parameter estimation, but there are other methods. Yeah? So there's restricted maximum likelihood estimation, there is there is, if you want, there's neural network gradient descent, or ordinary least squares, these kind of probability-free methods, and then which are really hard to study analytically because there is no theory around them. And then there are things like methods of moments, which we will also mention, I think, in one of the Übungen. Yeah. So just keep in mind that maximum likelihood estimation is not the only thing, but by far the most prominent thing. And restricted maximum likelihood estimation is a kind of further development of maximum likelihood estimation. So we've seen that. Now, the big things in terms of the maximum likelihood estimators are its consistency and its asymptotic efficiency. And this is then, if you look at the slides of the lecture, this is the biggest part of this lecture, and it's discussed in some depth. So let's first have a look at the consistency. So we are, of course, in the setting of a parametric statistical model. We have our sample, which is distributed according to this, and we have the maximum likelihood estimator. Yeah, so that's the big difference to the criteria that we discussed previously. When we discussed the criteria, we discussed any estimator, be it derived by guessing, be it derived by methods of moments, restricted maximum likelihood, or whatever, or maximum likelihood. Here we are only looking at the maximum likelihood estimator. And here we actually understand the maximum likelihood estimator as a local maximizer of the likelihood function Ln. The reason why it's here not understood as the global maximum of the likelihood function is that the proof requires that it's at least a local maximizer, and it doesn't say anything about the global properties. That really goes then into mathematical subtleties that are based on conditions that you need in the proof. On the other hand, I had an earlier version of this lecture where basically this second hour was basically, the maximum likelihood estimator is consistent, so there exists a consistent sequence of maximum likelihood estimators, and this is said to be a consistent estimator. For proof, see that book. And the same I had for the asymptotic normality and efficiency. And then, because we are using specifically the asymptotic efficiency next week and the week after, in terms of Wald statistics, I thought, why not look into a proof? Then I realized when I looked into the proofs, they are a bit more involved than the other proofs that we looked at so far, and actually quite a bit more involved. So first, again, what does that mean? Well, in probability, the theta hat maximum likelihood estimator converges to the true but unknown value of theta. That's just the definition. This is, again, just the definition. And this is kind of the point. There exist proofs of varying mathematical generality and depth. This is, again, just what consistency means. So I looked into the books, and in the Wassermann, I really didn't. So the proofs are fairly similar. They all the books. So the simple. So they are the kind of specific proofs of the consistency, which work with this local maximization, and then there are more general proofs that go beyond assuming that the maximum likelihood estimator is a local maximizer. The problem with the local maximizer is that it's not unique. So to make that clear, so if you say the maximum likelihood estimator is a local, is the argument that locally maximizes the likelihood function or the log likelihood function, then of course your log likelihood function could have multiple local maxima, That means you could also have multiple maximum likelihood estimators, and then it's not unique and you're not really sure what you're talking about. So in essence, you want your maximum likelihood estimator to be defined as the global maximizer, so the unique maximizer of your likelihood function. But then the proofs get quite demanding, and this I just didn't have enough time to really go into that. So I'm dealing here with these local maximizing proofs, and even those in the Wassermann, it's really short and it's really hard to get the idea. So I try to work a little bit with the held proof, and this is what I have on the next couple of slides. So of course these proofs are not exam relevant. Of course you will not be asked about these proofs. But on the other hand, I thought just now saying, well, the maximum likelihood estimator is consistent. The question is then, why? How can one see that? And this is what I try to discuss on the next couple of slides a little bit, and also give you a feeling of that this really gets a little bit more mathematically complex. So how does this proof work? And here there's a lot of text, but I will read over it, and so to give you the idea. And it's interesting if you find these kind of things interesting. So the idea of the proof that you can find in the held book is to essentially just show that there is a maximum of the likelihood function in an interval around the true but unknown parameter value, for an arbitrary small epsilon with probability 1. So as n goes to infinity, so there are these, this is why this is always a little bit hard to study, because there are these multiple things that happen at the same time. So n goes to infinity, the probability of an event is going to 1, and this holds for arbitrary small epsilon. So the idea is to show that as n goes to infinity, an interval around the true but unknown value has there is a maximum in that with probability 1. So this is, at first it was a little bit, okay, what does this have to do with my maximum likelihood estimator? Well, of course, if you assume, or if under the Fisher regularity conditions, the likelihood function is continuous, then based on this continuity and the definition of the maximum likelihood estimator as a local maximizer, this means that the deviation of this maximum likelihood estimator from the true but unknown value always also gets small with probability 1. Maybe I shouldn't use this epsilon here. No, I can use this epsilon because it's based on this epsilon delta criterion of continuity, that these things in the value space of the function get arbitrarily close, and at the same time the values that happen in the input space of the function get arbitrarily close. So now, if there is this local maximum in this interval, then this means that also with probability 1 as n goes to infinity, this means that then also the maximum likelihood estimator gets arbitrarily close to the true but unknown value with probability 1 as n goes to infinity. And this is consistency. So the main part of the proof is actually not to show what's happening with the maximum likelihood estimator, but to show that there is a local maximum in this interval. Because this by continuity implies that the maximum likelihood estimator goes to the true but unknown value. Now, so that's the idea. Now, to show that there is a maximum of the likelihood function in this interval with probability 1 as n goes to infinity, it actually suffices to show that in the limit, the deviation of the likelihood function at the true but unknown parameter, sorry, not the deviation, the event that the likelihood function at the location of the true but unknown value of the parameter is larger than at a point somewhat to the left of it, and a point somewhat to the left, to the right of it. So this is quite simple, because this is just some chalk. This is just to say that if you have a maximum here, then here this is a theta, and if you go a little bit epsilon in this direction, epsilon in this direction, here, the value of the likelihood function gets smaller. And this happens with probability 1 as the number of data points increases. And both of these arguments one can show kind of equivalently. So in the help book and also then on these slides, the focus is on showing that the probability of the event that the likelihood function at the location of the true but unknown value is larger than the likelihood function at the location of the true but unknown value minus a very small epsilon goes to infinity is 1. Maybe you wonder about why this is an event, so why I'm talking about this Ln theta larger being is an event. And of course, there you need to keep in mind that likelihood functions are essentially random functions, because they are always specific to a specific data realization. Yeah, so they are the probability of a specific data realization for a specific parameter setting. And if you now have different data realizations in the frequentist setting, then of course you also have different values of your likelihood function at a fixed parameter. Yeah? So this is why you have why you can talk about the probabilities of these kind of things, because it's not because this is these are essentially, so the Ln at the location theta is a random variable, the same as Ln at the location theta minus epsilon. So one can talk about the probabilities. And now to show that this limit of this event attains probability 1, this can be done using the weak law of large numbers, which we established, and something else, namely the positivity of the Kullback-Leibler divergence. And I appreciate that I haven't introduced the Kullback-Leibler divergence yet. You might know what that is. So does anyone know what the Kullback-Leibler divergence is?
Earth moving distance. I mean, it's not symmetric, because the two if you swap the position of P and Q, they are not, but they are usually to evaluate the difference between two distributions, even though they are the intersection of their distribution has a measurement of 0.
Yeah, so it's not identical to the Earth mover distance. That's a different distance measure on probability distributions, but you're right, it's a distance measure on probability distributions, and it basically quantifies in a specific way how different two probability distributions are. And the thing is, this positivity means that it's if the two distributions are identical, then the Kullback-Leibler divergence is 0, and if they're non-identical, it gets larger than 0. And we will see the Kullback-Leibler divergence later on when we talk about Bayesian inference and variational inference. So I will, I think next year, because I didn't know that this will come up at this point, so I didn't put it into the lecture 5.
Technically, KL divergence is not distance, because it does not separate. Yeah,
it's not a metric.
Yeah, it's a metric.
Yeah, it's not a metric, but intuitively it's a difference measure. So so these are the two things that you need to understand why this probability being 1 holds. So you need to understand the weak law of large numbers, and you need to know what the Kullback-Leibler divergence is, and that it's positive. So Then if one has these kind of two properties, then or these kind of two things in the back of your head, then the way that the proof works is to first reformulate this event of interest. Yeah? So we want to say something about the probability of this event in the limit of large data, in the limit of large sample sizes. So we can reformulate this event as follows. So, or this inequality as follows. If we have this, we can of course multiply in both sides with 1 over n. That was an email. Then what do we have here? So here we've multiplied with 1 over n, and then we just put the one of them on the other side, and see that this is larger than 0, and then we actually write out what the definition of the so I ought to introduce the log. Sorry, I didn't say that. So we introduce the log on both sides, and we introduce 1 over n on both sides. Then we put everything on one side, and then we write out what actually the log likelihood means in both cases, and then we use the log probability, log and properties, and put this together. So this is just reformulating this event, very elementary algebraic manipulation. Yeah.
So why do we use the 1 over n?
The 1 over n, this will, so while we're doing like this, this is essentially here. Of course, we're doing it so that we can apply the weak law of large numbers. Because the weak law of large numbers says that if we, that's about sample means, of course. So if you have the mean, so you sum up things and you divide by the number of terms that you sum up, this converges in probability to the expectation of this. So that was the weak law of large numbers, which is then, after reformulating this event like this, basically just used here. So this is the average of the log of these values here, and this, by the weak law of large numbers, converges in probability to the expected value of this. Yeah, that's why this reformulation is there. And the reformulation has another property, namely that this term here, if you look at the expected value of it, this is just the Kullback-Leiber divergence between p theta x and p theta minus epsilon x. So if you write this out, you see that this is just the KL divergence, and KL divergence just defined as the expected value of this divided by this. And if they, and by the Fisher regularity conditions, of course, these theta and theta minus 1 are different PDFs. So the KL divergence positivity then ensures that this term is larger than 0. So this is where the KL comes in. And this is then just stating again what we've seen. So we've shown that this average converges in probability to a value larger than 0. This corresponds then to a limiting probability of 1. So this is, again, going back one slide, this thing here is strictly positive. So this is always larger than 0. So this converges to something larger than 0 in probability. This means that the limit of the probability of this thing being larger than 0 is 1, and this thing here was just our reformulation of our event, that the likelihood function at theta is larger than the likelihood function at theta minus 1. So we've shown that this happens with probability 1, and hence we've shown that this event that is larger than this has probability 1. And and that's the way I simplified this whole thing as much as possible. It's not, I mean, if you're doing mathematics, this is of course just, you do this for breakfast in the first 10 minutes to get up. But as we of course are not always doing that detailed math, it's maybe looks a little bit a lot, but yeah. So the main point again is that you prove essentially that there is a local maximum in an interval symmetric about the true but unknown value. And because because the likelihood function is continuous in theta, and the maximum likelihood estimator is defined as a local maximizer, this establishes the consistency. Again, this does not establish, or this is not under the assumption that of a unique maximum likelihood estimator. Good. Yeah. So this was kind of like a little bit of a really trying to understand why the maximum likelihood estimator is consistent, and I would say from this you can understand that a little bit. The proof is not as constructive as you sometimes would like proofs to have, so it's more kind of a proof where you use everything at your disposal to make it work, which is then not that straightforward, but at least it's a proof. And again, you can look into this in much more detail, in much more generality in your free time when you're not doing assignments in bioinformatics. The other thing is the asymptotic efficiency of the maximum likelihood estimator. So consistency we've now seen, and now we are talking about the asymptotic efficiency. The statement is, of course, that the maximum likelihood estimator is asymptotically distributed according to a normal distribution, with expectation parameter being the true but unknown parameter value, and variance parameter being the reciprocal of the expected Fisher information at the location of the true but unknown parameter value. This is, of course, just the definition of asymptotic efficiency, and the claim is now that this holds for the maximum likelihood estimator. This is, of course, important, and we will use this for confidence intervals and hypothesis intervals, because hypothesis tests, sorry. Because to create confidence intervals, you might recall from undergrad statistics that you, for example, for a 95% confidence interval of a normally distributed thing, you then somehow take values that you get from the t-distribution, and with these values you multiply, so something like 2, you multiply the standard error. So I hope you remember something about confidence intervals in this regard. This is, of course, in the case that you have analytical solutions for the distribution of your estimator. Now, what this is saying is that regardless of the distribution that's actually happening, if you're using a maximum likelihood estimator in the limit of large sample sizes, this maximum likelihood estimator will have a normal distribution, so you can use the parameters of this normal distribution to construct confidence intervals regardless of whether you actually know the underlying distribution of the data, like in the t setting, for example, but just because you used a maximum likelihood approach to derive this. So, for example, if you do maximum likelihood estimation in your own model something, and then you get a maximum likelihood estimate for your parameters, you can just draw confidence intervals on this based on the assumption that the maximum likelihood estimator is normally distributed if you're confident that you have a lot of data and you don't have a better idea, essentially. We will see that in detail about the confidence intervals next time, and how to also use this in hypothesis testing the time after that. But these will always then be based on this property. So this is why I also for this include a proof here. This is what I just explained. So we will use this property in lectures 9 and 10, and maybe after that. So this is why I also try to look a little bit into why this holds. And I think it's actually a little bit more straightforward why this holds, not completely, but a little bit. So again, the claim is maximum likelihood estimators, if you have large sample sizes, have a normal distribution. Yeah. So if you think you have a large sample size. You think that your statistical model allows you, in theory, to sample again and again. You look at the distribution of your estimator. This is a normal distribution. I hope this frequentist intuition is clear to you, why you have these distributions. No? If not, ask. But these distributions are hypothetical distributions, right? So, and they are not Bayesian distributions. So what's the proof here, and what's the idea here? The main thing is to show that, not quite sure why I have these brackets there. I think because I'm missing something. This is why the brackets are there. This is a typo. There needs to be a minus theta in the brackets here. Here we need minus theta. This is why there are also some brackets around this. So let's write this up here. It's supposed to say Jn theta times theta ml, so the maximum likelihood estimator minus the true but unknown parameter. This is asymptotically distributed according to a standard normal distribution. And then what you can do informally, and the informal thing is here that, of course, if this holds asymptotically, that if this holds asymptotically, which here corrected, I need to correct in the tech version, if this holds asymptotically, then it's not really clear that also if you do a basically linear transformation thing where you say, okay, if this is standard normal, then if I look at only this, then my minus theta here will be the expected value, and the square of my factor here, so that was this A when we looked at linear transformation of Gaussians, will be the variance. This is true if things are in the non-asymptotic scenario. This is where we established them. Whether that holds in the asymptotic scenario, you would have to show, because there's an operation behind this A tilde. However, we let that fall under the table, and intuitively, if square root Jn theta times theta ml minus theta is distributed according to standard normal distribution, then theta ml is distributed according to a normal distribution with this expectation, this variance. The proof, however, is concerned with this entity. Yeah? So formally, you would have to, from this and the properties of asymptotics, go here. Now, to show that this holds with our little minus theta in there, one needs a couple of things. So one needs the continuous mapping theorem, one needs Slutsky's theorem, one needs the fact that in distribution, the score function divided by square root of n converges to a normal distribution with the expected Fisher information of a single variable as variance. And one needs the convergence in probability of the Fisher information, not the expected Fisher information, to the expected Fisher information. Yeah? So ideally one knows what the continuous mapping theorem is, what Slutsky's theorem is, and why these things follow. So this is then what is introduced on the next slides. So continuous mapping theorem, it's actually a result from 1943. So the terms of mathematical results we discuss here, they are not that old. Yeah. So this is not mathematics that already Archimedes in his little garden or wherever he worked did. This is kind of 20th century mathematics. Yeah? So it's not completely like what Gauss already knew, because he could sum up the numbers from 1 to 100 in 10 seconds, because he had this thing. So this is what I'm saying here. It's quite modern. This is by Abraham Wald, and what the continuous mapping theorem says, which of course we don't prove here, is something about the convergence types under functions. So if you have convergence in probability of xn to x, then if you apply a continuous univariate real-valued function on both sides of the statement, then this also holds. And again, you would need to show that based on the definition of convergence in probability, but we don't do that, and we just establish that this holds. So essentially, convergence in probability is invariant to the application of continuous univariate real-valued functions, and the same thing holds for convergence in distribution. And for proofs, look into this paper. Slutsky's theorem that came earlier actually, but also just 20th century mathematics, is that if you have two sequences of random variables that converge in distribution and in probability to a constant, then if you add these two sequences, of course you would have to define first what you mean by addition of sequences, but that's of course yeah, I hope you know that from analysis. On the other hand, it's also quite straightforward because it's just an element-wise operation. Then this added sequence converges in distribution to x plus a, which is also kind of, so this is kind of invariant under addition, if you want, and the this also for multiplication. So this needs to converge in probability, this in distribution. The results are then about convergent distributions. So essentially, continuous mapping theorem and Slutsky's theorem are simple calculation rules for under probabilistic convergence. And yeah, one can prove them. But we can't all be Peter Scholze. We also have to work. So then the next two building blocks are the convergence in distribution of these terms. And they are relatively straightforward. So because this is about the score function. And of course, yeah, one thing that I didn't include there but mentioned is that if you have the score function of a random sample, this corresponds to n times the score function of the random variables that make up the random sample. Yeah? So all these random variables have the same distribution, and if you multiply their score functions, you get to the score function of the random sample. So this we can rewrite as this. What we actually discussed in some detail is that the expected value of the score function is 0 and the variance of the score function is the expected Fisher information. We looked at proofs of that. So then with the central limit theorem in this case, which we have in lecture 5, and one variant of that, we have that a term like this converges in distributions to a normal distribution with these parameters. So this is a consequence of the central limit theorem, and this then in our case means that this kind of thing converges in distributions to normal distributions. In a way, I mean, it's about asymptotic normality. Where else than from the central limit theorem should this normality come from? Yeah? So central limit theory means something converges to normal distribution. Now we're saying that the maximum likelihood estimator distribution converges to a normal distribution. Well, it has to do with the central limit theory. That's not the biggest surprise. The question is, where exactly does the central limit theorem come in? Convergence in probability of the Fisher information divided by 1 over n. Again follows, this follows I think with the weak law of large numbers again. Here again you have kind of an average. We know what the expected value of the Fisher information is, namely the expected Fisher information. And if we then apply this logic, if you apply the weak law of large numbers, which says average converges to expectation, in this setting, then we get average converges to expectation in probability. So this is how these two things are established. then we are finally in a position to show that with our little minus theta in there. And yeah, I think in my head I haven't quite worked out why we can neglect the fact that we're actually using a Taylor approximation. So if you so what happens is that we show this under the assumption of a Taylor approximation, namely a first order Taylor approximation. And currently I think I'm not quite sure why we can ignore the fact, or what about the error and why the error is 0. I mean, there will be mathematical arguments for that, but please don't ask me what the mathematical arguments are, because I don't know. So the way to show this works is that we start with a Taylor approximation, first order Taylor approximation of the score function in the expansion point of the true but unknown parameter value. Yeah. So we write the score function with respect to theta tilde. Theta tilde just is there to dissociate this from the true but unknown value, which I denote by theta. And I didn't want to go away from this convention here. So we rewrite the score function in a first order Taylor approximation. And then, of course, the first derivative of the score function is the Fisher information, because that's the second derivative, the second negative derivative of the likelihood function. This is also where you get this minus sign from. And if we now substitute, and if we now look at the, maybe that, no, I'm not sure. If we now substitute the maximum likelihood estimator in this Taylor approximation, then with the properties of the maximum likelihood estimator, we can reformulate this Taylor approximation fairly closely to what we will be interested in here, if I hadn't forgotten to put in this minus theta. So just by the Taylor approximation and the fact that the score function at the location of the maximum likelihood estimator is 0, because of course the derivative of the likelihood function at the maximum likelihood estimator is 0, because it's maximizing the likelihood function. This is why you get the 0 there. You can reformulate that and get this. And then, yeah, just by appreciating this little n thing here, you get this being approximately this term times this term. And of course, these two terms we studied previously. And then, based on Slutsky's theorem, that's awesome. It's really math stuff. Based on Slutsky's theorem, it follows directly that this converges in distribution to these two things. Then again, with the transformation of normal random variables, again applied a little bit intuitively, you get the convergence in distribution to this. And this is what we wanted to show all the time, but I had it written up a little bit messy. Yeah. So what is the lesson we learn from this? Of course, the normality in the end is due to the central limit theorem, but the question is, where does this central limit theorem come in? It has to do with the weak law of large numbers and with the fact how you can compute and calculate with convergences and probabilities. And then there is this first order Taylor approximation that this rests on. And that means this is only true with some error. The question is then what happens with this error under these convergences. And I guess this is why the Taylor approximation then doesn't matter anymore, because under convergence the error that you introduce by the Taylor approximation goes to 0. I would assume that this is one of the reasons, but you don't actually find this in the books. So that was a lot of fun. And this is the summary and the bottom line, of course, for everything that we did today. We introduced asymptotic statistics and these criteria for the properties of estimators if the sample sizes get large. So if we are in 2019 where the sample sizes are large and you need SQL to download some data, because the sample size is so large, we are in this, so it's important. So we are in this age of big data, so it's important. And these are the criteria in the large sample size limit, and maximum likelihood estimators, which are our favorite estimators, are asymptotically unbiased, consistent, asymptotically normally distributed, and asymptotically efficient. Yeah, so that's the bottom line. Good. Any questions? I know these proofs are not, it's not that much fun, but on the other hand, yeah, what can you do? You either say the maximum likelihood is normally distributed, and the question is why, and then you say it's shown by math. Or you look a little bit into why, and then you basically, what you always do in math, you just put the problem somewhere else. Yeah? So you say, yeah, that follows from Squeeze Theorem and continuous mapping theorem. And then, of course, you can say, yeah, but continuous mapping theorem, why does this one? And so you get into these kind of recursive depth problems. But on the other hand, we've seen where the central limit theorem come in for this, and we've seen where the weak law of large numbers comes in for consistency. So we kind of have a little bit more expanded and better understanding of how these things sort. Good. So I think now from after this one, so this the estimated properties, this was quite theory heavy, and from then the next lecture on, we do kind of more the applied frequentist statistics, which doesn't say that the math is now gone and we just use SPSS from now on, but at least it will be things that you see every day in data analysis, namely confidence intervals, hypothesis tests, and whatever comes after that. Yeah, any questions? No? Good, then let's do exercise.